All right. Thank you. And after much delay, I can hopefully answer this question that Carlos prefaced by saying would be the one I would be answering, which is a bit unfortunate because the very first thing I'm going to tell you is that I don't really have a good answer to this. But what I can say pretty confidently is that this is perhaps the most profound question in cosmology today. Okay, so what is the state of cosmology today? Well, we think, as we've seen several times before already, the universe started from a Big Bang, expanding from quantum fluctuations, and then over the course of billions of years, we have the interplay between dark and ordinary matter forming the stars and the galaxies, creating the large-scale structure of the universe, eventually forming planets and life where we live. And what you'll notice in this beautiful image created by NASA, that the sort of space within which all of this is happening is constantly getting bigger. Okay? And so this brings us to one of the most important things we have come to learn in 20th century cosmology, as Jim said, that the universe is expanding. Now, a lot of what I will say from here on are kinds of repetitions of what Jim said, so treat this as a revision lecture before the exam at the end of this talk. So, how did we get to this point? It's worth taking a step back in time and focusing on the contributions of four individuals who I think are very formative. We have Einstein, who, of course, came up with his theory of general relativity, encapsulated in the form of this equation, where you don't really need to know the elements of it specifically, but the left-hand side in red is basically telling us about the geometry of space and time, and the right-hand side in blue tells us about what space and time is made of. So rather eloquently, you can describe this as space-time telling matter how to move, and matter telling space-time how to curve. Now, in 1912, there was rather an important discovery made by Henrietta Leavitt at Harvard College Observatory, when she realized that there was a distinct relationship in the pulsation periods of a certain class of stars called Cepheid variables and their luminosities. And what that does is, by being able to measure luminosities and brightnesses in cosmology or in astrophysics, you can start measuring distances. So Henrietta Leavitt's period luminosity relationship helped us actually chart and compute distances to distant objects for the first time. So now we've heard the story of Hubble and the idea of the expanding universe through the measurement of galaxy redshifts. But actually the person who maybe deserves some of the credit behind this is someone before Hubble as well, a gentleman named Vesto Slipher, who had actually very good data regarding the motions of galaxies and their distances 5 years before Hubble's sort of exposition of the fact that this might relate to the fact that the universe is expanding in 1922. So how is a measurement like this done? Well, it basically relies on this idea that, imagine we are observers on Earth, and we are observing a galaxy that is moving away from us due to its own peculiar motion or due to the expansion of space and time. The light from this galaxy will slowly get stretched by the expansion itself towards redder and redder wavelengths in this phenomenon that we call redshifting. And the further the galaxy moves, the faster it appears to recede. And this is what we have observed happening to most galaxies on average. The relationship between the velocity and the distance that this galaxy is at is basically given by a particular number called Hubble's constant, which tells us about how fast the universe is expanding. Okay, so the universe is expanding, but a very reasonable question to ask is, has this always been the case, and will this continue indefinitely? Okay, so of course the growth and the evolution of the universe through Einstein's equations is some combination of the geometry of space and time and what space and time is composed of. So we need to solve Einstein's equations to know the answer to these questions. And over the course of a few years, some of these solutions came rather elegantly through the work of Friedman, Lemaitre, Robertson, and Walker. And essentially they said that the evolution of the universe is this constant tug of war between expansion and gravity. And in particular, you can say that all of this depends on some kind of combination of what the universe is made of in terms of how much radiation there is, how much matter there is, so basically gravity, and what the shape of space and time is. Is it flat? Is it curved like the surface of a balloon? Or is it something more exotic? Now, fast forwarding some time, as we heard from Jim, by the 1990s, there was pretty good evidence that, well, the amount of radiation today is pretty small. The universe is seemingly quite flat, and the density in matter was, of the order of 20 to 30% in some particular units. So you would think that if this matter, the gravitating part of the universe, is what dominates, then a universe, even if it's expanding now, should eventually start contracting, because gravity will resist expansion and slow it down. And so you can go ahead and say, okay, let's try and map this expansion and measure cosmological distances to even larger scales than we have ever done before. And to do that, you need something really bright so you can see it far away. So supernovae turn out to be a rather important candidate for that. And so these two teams, the Supernova Cosmology Project and the HiZ Supernova Search Team, essentially went ahead to measure what in their papers they actually called the deceleration parameter of the universe. Because, of course, if matter is this dominant entity, then it should be decelerating the universe. So you would measure positive deceleration, meaning that the universe is slowing down. So how do you go about doing this and using supernovae to tell you about this? Well, imagine we have space and time, right? And we go to our favorite local corner store and buy a light bulb. And the light bulb on the package tells you how brightly it burns. And so we know what its intrinsic brightness is. Now imagine taking this light bulb and slowly moving further and further and further and further away. You would expect the brightness of this light bulb to start dimming. And because you know exactly what the manufacturer has said is the intrinsic brightness of this light bulb, you can work out how far away this light bulb is just based on how much it has dimmed. So this is basically the case of supernovae, a class of objects called standard candles, which means we can use objects of some known intrinsic brightness to calibrate distances. And this is basically what these supernova cosmology teams are looking at. Now, this is rather a more fraught exercise than just measuring supernovae, and it actually relies on being able to calibrate and measure distances on a variety of scales, because you have to know exactly what is a known relationship between distance and luminosity and what we're actually trying to measure. So what actually the teams do is calibrate distances firstly on scales nearby to us, using things like Cepheids by looking at their motions in the sky that can tell us about what their distance is. You can then calibrate those distances to Henrietta Leavitt's period luminosity relationship, then take these Cepheids and look at other galaxies that have Cepheids to calibrate distances to those galaxies, identify that there are supernovae there, so then you can then take those supernovae based on the calibrations you've done with the Cepheids and look at even more distant galaxies. So there's a hierarchy of knowledge that you build up from the nearby scales to the most distant scales, and this process is called measuring the cosmic distance ladder. So, what is the end result that people came to? Well, if we have a measurement of how bright or how dim supernovae look as we go further back in the past, if things have no change at all, they lie on essentially zero, and the measurement, unsurprisingly, came to look something like this, where the supernovae data are now shown in these white symbols. This is a slightly newer version of the data that Jim showed from 98 and 99. But essentially, the supernovae data seem to be consistent with a model where the universe was decelerating in the past, but is accelerating now, because the observed dimming of the supernovae seem to be getting faster and faster. And that's basically, to show you a real pie diagram, is how we come to this picture here of what the composition of the universe is. So this was made by a colleague of mine for Pi Day, in fact. And we think that dark energy dominates to about 69 to 70%. So there is now overwhelming evidence for the existence of dark energy, okay, not just from supernovae, but from things like the distribution of galaxies in the sky, the microwave background, and things like something called the integrated Sachs-Wolf effect, which basically tells you about differences in temperature in different parts of the sky as photons stream through the expansion of the universe. So, what is it? Okay? So perhaps the leading model for accelerated expansion is the cosmological constant that we obviously heard about before. And its origins, as Jim sort of alluded to earlier, was for rather a different reason, which is if we go back to this famous equation again, which tell you about the contents of the universe and how they relate to the geometry of the universe. Okay, as James said, this was rather a bit of an annoyance for Einstein because this led to a dynamical universe, one that is changing. And even though this was in 1917, when perhaps he might have known that the universe is actually expanding, looking at Slipher's data, which existed at that time, he didn't think that was a possibility, so he wanted to make this universe a static, unchanging entity. So what does that look like? Let's take the universe, represented here by the Ogden Centre, and a universe that is made up of mass that has gravity will have the tendency to collapse under gravitational instability, gravitational attraction. So what you can do is to try and balance things out. You can say, let's say that space and time has a fundamental property to it, the so-called vacuum of space, which we know through quantum physics, that causes the space-time itself to repel gravity because it has an anti-gravity property. So the vacuum of space and time will counteract this and cancel out perfectly gravitational collapse, leaving you Einstein's static universe. And this was basically added on as a term in the equation, the so-called cosmological constant, to try and perfectly cancel things out. And it is this same term that we can now use to try and understand accelerated expansion, except that in Einstein's case, where things cancel out perfectly with gravity, we just say that it's now a factor of 3 times bigger, which is why we have acceleration. So, why does something that is constant become the dominant entity in our universe? Well, let's think about how matter and radiation actually dilute as the universe expands. So we have time on the x-axis, or the size of the universe, and the amount of matter and radiation. This is sometime today. And as the universe expands, you would think that the density of matter and radiation will start to decrease because you have the same amount of stuff spread over a larger volume. But a cosmological constant, by definition, is constant, and it stays there, kind of silently waiting, and then all of a sudden it crosses over matter and radiation around about 5 billion years ago till it becomes the dominant entity, about 3 times the matter. So this actually poses one of the interesting conundrums about the cosmological constant, which is that why do we live in this time now that the cosmological constant is dominant? And why did it not happen earlier, which might have meant something more catastrophic perhaps for the existence of life? So you can ask, well, how much vacuum energy do we need to actually cause all of this stuff to happen? Well, from astronomical observations, we can estimate roughly that the density of the dark energy is around about 6 times 10 to the minus 27 kilograms per cubic meter, which is an exceedingly small number, okay? So if you were to take a room of this size, convert that density of dark energy into an equivalent energy, that is far, far, far less than the energy required to keep the lights turned on in this room. And so that's why dark energy has no real effect on this scale, because the density is pretty low. But if the vacuum energy is a prediction of quantum physics, you can try and calculate this density in quantum physics as well. And the number we get is around 10 to the power of 36, which, give or take, is quite a lot bigger than that previous number. This is a discrepancy of at least 60 orders of magnitude, which even for astronomers is hard to argue away, right? And so this is sometimes called the most embarrassing prediction in all of physics. So what else could it be? So there are some other alternatives to dark energy, to the cosmological constant. One particular example being something called quintessence, okay, which, if you know your Latin, which I don't, means the 5th element, right? So what this basically says is that dark energy need not be this vacuum, but an entity in its own right, a so-called scalar field, okay? And this scalar field, which is represented by the letter phi, has the properties that it permeates space, so it's all over. It is dynamical in nature in that it can change over time, and it can be inhomogeneous as well, so different parts of space can have different values of the scalar field. So a scalar field is basically something that just associates a number with a point in space. So kind of looking at a temperature map of the globe has a temperature associated with different points in space. Okay. Now these scalar fields have rather interesting predictions to them because you can, because of these properties, do lots of interesting things with them. So let's look at our familiar thing of time versus size of the universe. We have the Big Bang and then throw things out. Let's now put our supernovae data down, again represented by the Ogden Centre, where now we find that, at least in the cosmological constant case, it is consistent with the universe that was decelerating in the past. It is accelerating today, and if you extend that forward, you might have a universe that is continually expanding. But what scalar fields can do is actually say that we might have the same beginning, but dark energy might eventually blow up and take with it our Ogden Centre in something called the Big Rip, or dark energy can change its form in the future and also take away our Ogden Centre in something called the Big Crunch. So one of the reasons why we should continue studying this is only to learn how best to protect this building we all love. But perhaps it is that gravity itself is not quite right. Maybe Einstein's theory requires some modification. And this basically takes us to the last thing I want to talk about, which is modified gravity, which basically says that maybe throw away lambda, and we just need to augment Einstein's theory with a greater and better theory of gravity from which accelerated expansion comes out naturally. Now, if you're of the faint-hearted nature, I would ask you to avert your eyes now, because the landscape for what this other stuff could be is really quite vast. But Durham, in the ICC, has actually carved out a niche as one of the world's leading experts in simulating these in a variety of different cosmological settings, including the predictions of galaxy populations as well. So finally, how do we test dark energy? Okay? The best tests, in my view, probably come from looking at the distribution of galaxies in the night sky, with future galaxy redshift surveys that will map the three-dimensional positions of galaxies across a vast range of scales. Because it is this pattern of distribution that encodes within it the entire history of the interplay between gravity and expansion. And Jim talked about this before, but there is this particular feature that is imprinted in the galaxy distribution at final time, which is basically a remnant from the very initial conditions, the so-called acoustic oscillations, which means that at present day, there are preferential distances over which galaxies can be found to be separated in. So if you were to actually compute how strongly galaxies cluster as a function of their separation, you would find that they cluster strongly on small scales, it decreases, and then all of a sudden there's a big bump at a particular scale, which we call the baryon acoustic oscillations, discovered by Daniel Eisenstein's group, but also here at the ICC in 2005. Thanks to Sean Cole and the 2DF survey. And so we can use these BAOs, as they're called, as a standard ruler. So we heard about standard candles. These are standard rulers to map the expansion of the universe as a function of time and learn about dark energy. One of the surveys trying to do this is the so-called Dark Energy Spectroscopic Instrument Survey, or DESI, which Durham is a big member of, having been involved in the construction of some of the instruments themselves, and a wide variety of other programs as well, some of which are listed here. So, in my last slide, here are some open questions that still remain, which I'm sure we will answer in due time. So, number one, how do we resolve this enormous discrepancy between the theoretical and the predicted, perhaps, value of the vacuum energy? Does the dark energy evolve in time? And if it does, is that a reason why different ways of measuring the value of the Hubble constant using late time or early time cosmology gives us different answers? Are there deviations from general relativity on cosmological scales? And if there are, then what are the unique signatures that we can look for that will help us eventually pin down the true nature of gravity? So I'll leave this with you to think about, and that's the end of my time. So thank you.
Thank you, Sownak. We may have time for just one question. Someone has a burning question they would like to ask. They haven't answered any of your questions up here. I'm sorry.
Makes my job harder, I think.
I'm sure you can catch Sownak around
Yeah.
after the session. So let's thank Sownak again.